Alrighty, good afternoon. Happy Friday, happy end of week 8. Alright, so hopefully everyone knows Monday is a holiday, so no Clark classes on Monday, which means I won't see you again until Tuesday. So we got a 3-day weekend from Clark. Alright, any questions up to here? PA5, networking, that kind of stuff? Anything you want to go over? How would you envision setting up the thread class in the project? Um, so the threading I'm picturing as sort of managing all of the network stuff, right? So depending on which side you're on, whether you're the client or the server, and remember there's a radio button you use to select before you create the network connection. You say which end of that you're going to play. So on the server side, eventually there's a start button which creates a server socket, calls accept, and then when you come back from accept, you've got a socket for communicating with the client. So, socket equals accept. And at this point, it's probably a good place to start up the network thread, or maybe start it up earlier and do your socket connection inside the network thread. But somewhere definitely before you begin playing the game, but after the panel has been constructed. So you've got a choice, right? But let's say in your JPanel constructor you decide to create a net thread object, so a thing that extends thread, and then call it start method. And what that can do in the start is you could go ahead and open a connection right away, but yeah, don't do that when the panel constructed. Wait till you've selected that you're the server, and the start button really says, I've made my selection. If you say I want to be the server, you get a start button, you click it, that sort of locks in that choice. If you want to be the client, you switch the radio button to client, and now you've got a connect button. You put in the host name, you say connect, and so probably inside, either the start button or the connect button, go ahead and make the thread. So create NT, which is a new net thread. And when you construct that thread, maybe pass an argument to the constructor. Tell it whether it's the client or the server. If it's the server, go ahead and make a server socket and accept a connection. If it's the client, go ahead and try to connect to the local host that you've specified on your JPanel or your JFrame, and try to establish that connection. And then, inside this net thread, swap names. So read a name and write a name. And don't get deadlocked on that, right? If both the client and the server try to read the name from the other side first and then send their own name, you're going to have deadlock because you're both waiting to receive the name. So maybe decide that, if you're the server, you're going to send name and then receive the name from the client. And if you're the client, maybe decide you're going to receive the name from the server and then send your own name. So you got to have some kind of handshaking. And then it's mostly just sending those clicks. So if it's your turn, which it will be in the server initially, you don't do anything until you click a mouse and you call the send XY method in the net thread. If you're the client, you're not going to do anything And the first thing you're going to notice is a message coming in from the net thread, and pass that to your click code. So yeah, I would set these up probably like in the handler for the start button or the connect button. If you choose client and you say connect and the server is not running, that's a user error. You're allowed to say, you know, no connection possible and just exit the program. So the understanding is whoever's going to be on the server side will hit their start button before whoever's the client hits their connect button. So that just has to be set up by the people playing the game. Otherwise, right, so if we don't have a server and you try to create a socket and connect to port 1234, it'll come back with an exception saying basically that it can't make that connection. And your only choice at that point would be to you know, just print an error message and exit the program, which is what I suggest you do. Or, you know, print a message saying connection failed and give them the option of clicking the button again, or go into some kind of wait loop and keep trying. And I would just exit and say, you know, silly user. Welcome. Don't underestimate the power of using Telnet or something like that when you're developing this, to develop the server first and then use Telnet to play the client side. That can help you sort of develop it in pieces. All right, anything else? So let's continue talking about dining philosophers. So remember, this is our thought experiment for resource sharing. So you got a bowl of apparently blue noodles, and you have 5 philosophers. Chopstick in between each. And the goal is for the philosophers to be able to eat for a while and then talk for a while. To eat, they need to have 2 chopsticks, one from each side. Once they have 2 chopsticks, they can eat as long as they want, and then they can put down both chopsticks and talk. And so the thought experiment is to think of algorithms that you can use where each philosopher is using the same algorithm in such a way that everybody manages to eat some and talk some and so on. And so we started with kind of, you know, a first order attempt at this, which was an algorithm like, everybody see if you have a chopstick on the left, if you do, pick it up, and then see if you have a chopstick on the right, and if you do, pick it up. And if at any point you don't have the chopstick you need, just wait a little bit and then check again, right? And we saw that if all 5 philosophers start at the same time, we end up with a deadlock situation. We end up with a situation where each philosopher picked up the stick from their left, and now each philosopher is at the point of their algorithm where it's saying wait for the stick on the right to be available, and that's never going to happen, because the only way that this philosopher is going to see a stick on their right is if this philosopher puts down their left chopstick, and that's not going to happen until they pick up their right stick, eat for a little while, and then put down their sticks. And they can't get their right chopstick until this philosopher puts down their left, which will only happen after this philosopher gets the stick on the right, which only happens after this one gets their stick on the right, which only happens after this philosopher gets their stick on the right, which this philosopher is holding. And so this is classic deadlock. You have 2 processes, 2 threads, and each needs something that the other has. And neither is going to give up their resource until they get the resource that the other one is waiting for. And it's impossible to make progress. So how could we modify this algorithm to avoid deadlock or to break deadlock? Any ideas? So you could make them wait random periods of time. Um, and for that to happen, you'd also need them to well, maybe. So we could simply wait a random period of time in the beginning. And in that case, this philosopher might, pick up their stick on the left, pick up the stick on the right. They can start eating. This one was waiting a little bit before they tried to get the stick on the left, and now they're unable to get that. So they won't pick up this stick either, which means this philosopher may be able to pick up these, and so on. So that can work in some cases. The challenge is that sometimes it won't work because the random amount of time that they wait is random, and it's possible that you might still have all 5 philosophers try to pick up their left stick at the same time, and then you got the deadlock situation. Could you have a third party distribute them? So this is one way out of this quandary, is to have something like a wait person or a centralized controller that basically says, okay, you can eat now, you have to wait, you have to wait, you can go ahead and eat, you have to wait. So if you have sort of a third party that can look in and see where the resources are, see who's eaten recently, who hasn't, that third party can do arbitration and help mitigate this. Or something like a token ring, right? Which you can use to implement round robin, I think. But something where you have some kind of higher level control. That will work in this situation, and if you're in a multi-processing situation, a threaded situation, where you can control these threads from some central location, that's great. But there are some cases where that won't be possible. For example, if these processes were running on different machines, the question of being able to communicate with those machines in a way to find out the status of each job introduces its own perils. So good. What about other ideas? So you can, if you identify the philosophers, if you give them numbers, for example, you can come up with algorithms that might help you get out of the situation. For example, if I number these philosophers 0, 1, 2, 3, 4, right? I could say, look at the current time in minutes and take it modulo 5, and if that matches your number, you get to eat for 1 minute. And I would lose my parallelism in that case, but this philosopher would eat then that one, then that one, that one, that one. And you could modify this in ways so that you could have more than one eating at a time, but you would still avoid their deadlocks. Limit their time plus interleave their time in odd numbers. So if we give them numbers like this, right, we could say, well, we could be very explicit. We could say philosophers 0 and 2 get to eat for a minute. And then when they're done, we can say, okay, now 1 and 3 can eat, and now 2 and 4, and now 3 and 0. And we could, have a schedule like that that allows them each to get a period of time at the bowl and avoids resource contention. So if we can identify these, again, under usually some sort of external control, that can be a way out. Or each one starts 5 seconds after the other. So if we go back to that kind of first order version, which was something like this. Is there a stick on the left? If not, go back and try again. If yes, then is there a stick on the right? If not, go back and wait for it. If there is, eat. Return sticks. Wait for some period of time, go back up. So that was kind of our first approach the other day, and we can get into a deadlock situation if they all pick up at the same time. So a variation of this would be, see if there's a stick on the left. If not, just go back and wait for it. If there is, see if there's a stick on the right. If there's not, then let's return the left stick and go back up to the beginning. So now, everybody might pick up their stick on the left, but this philosopher gets the stick over here, checks for the stick on the right, isn't able to get it. They're going to put down both sticks. Well, they didn't get this stick, but they're going to put down the stick on the left. And so now this stick is potentially available for a philosopher 4. And so there, if you throw in some random time intervals, if instead of just going back and trying again, you wait some random period of time, if it really is a random period of time, there's a good chance that, everybody will pick up the stick on the left. None of them will see a stick on the right, so they'll all put their stick down that was on their left. And now they're going to each wait some random amount of time, and whoever decides to go first is going to see their stick on the left and also see their stick on the right, and they'll be able to start eating. But if they all ran this algorithm in sync, and if their random numbers that they were waiting were exactly the same, you get something like a deadlock situation, but something we call live lock. And the idea of live lock is that instead of just sitting here where you're spinning, right, you're actually changing state, but you're never getting beyond this part of your algorithm. So the effect is the same as deadlock, right? Basically, you can advance a certain amount through your algorithm and then no further, but you still see changes in state, right? You get the left stick, you try the right, you put it down, you wait, you pick up the left again, and so on. You're doing stuff, but you never get to the part of the algorithm where you actually eat. And we see versions of this in real life. So have you ever done this? You're walking down the hallway and you're walking on the right side and somebody is walking towards you and they're on the same side, and you get to where you're face to face with someone and you're expecting them to move and they're expecting you to move, and you just kind of stare at each other, right? That's a deadlock situation. Because my algorithm is, if there's nobody in front of me, take a step forward. If there is somebody in front of me, wait for them to move. Well, if this person is doing the exact same algorithm, then at the moment when we're face to face, we're both executing the same code. If there's somebody in front of me, wait for a second and then try again. And we're stuck. So that's a deadlock. The variation on that, which is more likely and more amusing, is your algorithm says if you're walking and there's somebody in front of you, go to the other side of the hallway and then go to the top of your algorithm. So I encounter someone in front of me, I move to this side, and if they have the exact same algorithm, they do the same thing. And now we're still face to face with each other, but on this side of the hall. And what does my algorithm say? It says if somebody's in front of me, go to the other side of the hall. So I come over here, their algorithm causes them to do the same thing, and now we're back in this situation. And it's not quite a deadlock. We're dancing back and forth, going, from one side of the hall to the other, but we never get beyond this point of our journey. And so that's live lock. So someone says, in case of waited for X time too long, re-randomize so it changes the interval. So if you can really randomize, then yeah, that will get us out of it. The trick here is that we're interested in processes running in, say, an operating system, rather than philosophers eating noodles. And so we don't want to wait longer than we have to. Um, we want a job to be able to continue executing as soon as possible. Um, and so we could say, wait from 1 to 5 seconds or something, but that's not really ideal. We really want these things to be able to execute as soon as a resource is available. So these situations occur, and they often occur unpredictably. You can write your code, and you saw this when we were running code yesterday or Wednesday to tally up numbers, right? Sometimes you run it and it works great. Sometimes it works great 5 times in a row, and then the next time you get a bogus result. And that's the problem. One of the problems with trying to find these issues in multi-processing environments is that your code may work great for a while. And then all of a sudden something happens and the system is frozen, and you go in and you look and it's something waiting for some resource, and why isn't it getting that? Well, if you can dig around far enough, you may find the thing that has that resource is also waiting for some other resource, and it can be really tricky to find these. If you can find what's going on, then figuring out a way to resolve it is usually fairly straightforward. But identifying the problem, can be a problem. And if you've got a server and it runs for a month and then hangs up, is it a hardware problem? Is it a memory leak? Is it a deadlock that occurs once a month? It can be tricky to find, and it's part of the fun slash kind of nightmare or headache of working with this stuff. So these are concepts we deal with. So deadlock and live lock, and starvation. And starvation might be a case where you have some algorithm that allows these two philosophers to eat, and then these two, and then these two, and then these two, and process 3 never gets a time slice. And you're not deadlocked, right? You're not live locked. The system is moving forward, but you've got starvation. You've got a process that's not getting enough time. And so this gets into scheduling methodologies for jobs on an operating system. So if you do an OS course, you'll study different strategies for how to schedule jobs, how to take a set of jobs that are sharing typically a CPU or some other limited resource, and how do you arrange them so that they each get a slice of time, they move forward efficiently, nobody starves, nobody hogs the CPU, and there's a lot of different approaches. So somebody mentioned round robin in chat, right? Round robin is typically, if it's a single, if only one process can run at a time, you would just go in order, maybe the order the job started in, and give each process a certain slice of time. And that can work pretty well, but it may work better if, for example, if you know how long a job needs, if you were to take the job that's going to run for the least amount of time and give that slightly higher priority. Because sharing the CPU among 4 processes is going to be more efficient than sharing it among 5. And if this job needs a very short amount of time to eat, if it's only going to eat a few noodles, right, give it a little higher priority, let it come out of contention, and then you're only sharing among a smaller number of threads or processes. So there's a lot of things you can do with process scheduling, and it's kind of its whole own discipline. All right, so any questions, comments about that? For PA5, we don't really need to worry about this too much. I would go ahead and maybe synchronize your code that can be called from your network thread or from your mouse handler. But other than that, you probably don't need to worry about this unless you're doing a lot with global variables, which probably you're not. All right, so let's just take a look at this in C. Because in C we've talked a little bit about creating processes back in 224 mostly. We talked about fork and execl and popen and the system call and so on and so forth. But that was mostly for the sake of you know, I'm doing something and now I want to do something different. So either I switch over to a new process or I start doing a new process until that finishes, and then I come back to where I was and I continue. Or, you know, in the case of the operating system, when somebody logs in, for example, I'm doing my thing and now I want to start a new process that's going to do its thing, and these are kind of independent of each other. But we could have, you know, a case where we have two or more processes in C that are trying to interact with a common resource. And we start to get into some of these same issues. So let's look at a simple example. So this is a main program. I have an integer tally, which I'm initializing to 0. And remember, when you call fork, what does fork do? What's the result of that function call? Makes a copy of the running program. It makes an almost exact clone of the current process. The code is the same, the variables are the same, the pointers are the same. Almost everything is identical. There's one difference in the clone versus the original. Do you remember what the difference is? Yeah, it was a long time ago. Yeah, so it's related to process IDs. So the child process is an exact duplicate of the parent except for the following. The child has its own unique process ID, so it's got a new process ID. The child's parent process ID is the same as the parent's process ID because, you know, that's its parent. It's got some other stuff in here, but the one that we're going to use is down at the return value. So on success, the PID of the child is returned to the parent, 0 is returned to the child. And this is the main difference that we use when we call fork. We look at the value that comes back from that function call. If it returns a 0, we know we're the child. If it returns non-zero, we know that we're the original, we're the parent. And that's really the only way that you know whether you're the clone or the original, is to check the return value from fork. And so this is you know, the secret code that tells you, are you the clone or are you the original? So we're going to call fork, and we're going to just check to see if the return value is 0. And if it is, that means that we're the child process. And so what we're going to do is we're going to go through a for loop. We're going to iterate a certain number of times, and I'm using a symbol here. So we'll iterate 10 times and bump up the value of this integer. And then we'll print a message saying, you know, the child's exiting, and we'll say what the tally was. Sharing a calendar in Nextcloud. I don't know what Nextcloud is, so that's okay though. If the fork returns non-zero, then we know that we're the parent. And so we're going to iterate the same number of times, increment the tally inside our for loop, and then say parent process exiting and show what the tally is. PA5 is due on Friday, I believe. So a week from today. Can someone confirm that? Just so I'm not like going off of memory. I got Canvas here. Let me look. PA5 is due June 4th. Yep, next Friday. Cool, thank you. And we switched and we're doing C, surprise. All right, so we're going to create a clone of the process. If we're the clone, we're going to iterate a certain number of times, incrementing tally, and then print out the value. If we're the original, we're going to increment tally that many times, print out the tally. So this is basically the same thing we were doing in Java, where we made 2 threads and each thread incremented our tally. So if we compile that and we run it, both processes report a tally of 10. And if we make this bigger, let's make it 1,000,000. Each process reports a tally of 1,000,000. So this is a distinction from Java. Even though our fork is creating a new process that's a clone of the original, it's really got its own essence. It's got its own copy of memory, and the values in memory will be the same as what they were before the call to fork. But once the fork happens, it's its own process. It's got its own process space, its own memory space, and you know what I could do in here is I could say, you know, if I'm the parent, if I'm the child, let's count by 7s. And if I'm the parent, let's count by 1s. Right? And so the child exited with a tally of 7,000,000, the parent exited with a tally of 1,000,000. So if we want to do what we were doing in Java with threads, if we wanted to share an object between 2 processes, we have to do some work to make that happen. Because normally these things have their own contexts. So let's take a look at sharing memory in C. So I'm not going to get too bogged down with the details of this. Oh, extra semicolon. I missed the extra semicolon. So I'm changing my tally to be a pointer to an integer, because what I'm going to do is I'm going to establish an area of shared memory. So you can look at the manual pages for this, but this is not something you need to know for this course. It's something you'll deal with in later courses. But we're going to basically ask for a chunk of shared memory. I'm asking for 32 bytes or words of shared memory. I'm going to make it readable, writable to the world. And then I'm going to try to attach this pointer to that shared memory. Okay, so the bottom line is this is getting a reference to a common location in memory that can be accessed from multiple processes. And if I'm the child, I'm going to take this pointer to an integer and I'm going to set that equal to something in this shared memory location. And I'll print out what the value of tally is as a pointer. And then I'll go ahead and I'll bump up the tally, you know, iter times, and then I'll print out the final value of the tally, and then this just detaches my variable from that shared memory. And if I'm the parent process, I'm going to do the same attach call. I'm going to attach my copy of this integer pointer to that shared memory. And the result is that even though I have 2 separate processes, each of them will have their tally variable pointing to the same spot in the machine's memory, not just their process memory. but the machine's memory. So that anything I do from one process to tally should get done to the other process. So if I run that, you can see each one, when it printed out the location of tally, it's the same location. And when the final process exited, the tally was up to 20. Even though the code said, iterate 10 times and increment tally, because I had two processes doing that, the total number of iterations on this one location in memory was 20, and we ended up with a value of 20. And if I do this 1,000 times, then, one of them bumps it up to 1,000, the other one bumped it up to 2,000. The Java pages will definitely tell you if things are thread safe. Or not, which they usually aren't. So let's iterate 100,000 times. And now you're starting to see some problems. So the earlier process to exit, no expectation what the final tally will be. But when the last process has exited, we would hope the tally would be 200,000, and it's not. Right? In fact, it's barely over 100,000. So here we've got a situation where the two processes are conflicting with each other. And remember, it's this business of, even though we're just doing an increment, it's actually a read, modify, write. And let's say, the first two things that happen is each process reads, and then, maybe each process modifies, and then maybe this process writes its value. Well, when this second thread writes its value, it's writing the value that it created here, which is based on the value it read here, which was before this process wrote its modified value, and so this read, modify, write has basically been nullified. So we didn't see this sooner because, if we're only trying to iterate 10 times, so this is a problem when, while one process is in the middle of a read, modify, write, the other process starts being in the middle of a read, modify, write. And if we're only iterating a few times, there's not a lot of opportunity for that to happen. The more times we iterate, the longer we're running, the greater the chance that this conflict is going to occur. Yeah. And so the bigger I make this count, the more severe it should be. But even if we make the number of iterations small, let's see if we can make this fail with just 100. So that seems pretty stable. All right. So if we wanted to avoid this, we can do something like what we did with Java, which is we can use some kind of locking mechanism. And the basic approach is, before this thread starts to do the read, modify, write, it asks if anybody else is doing a read, modify, write. And if nobody else is, it grabs a flag and holds that flag up and says, I'm the only one who can do this stuff right now. And if after this has started, this process says, hey, is anybody else doing a read, modify, write? it'll see this flag and say, oh yeah, someone else is, I'm going to have to wait. And then when this thread finishes, it puts the flag down, and the next time this thread checks, it says, oh, nobody's doing an RMW. Okay, it goes ahead, grabs the flag, holds it up in the air, and now it has exclusive access. I think that's partially because Java is running slower than C, and it might be at a finer granularity of time slicing. But yeah, I think that's interesting too, that comment in chat that with Java it seemed to misbehave at lower iteration counts. And I think there's probably some hints about how these systems are running. All right, so we want some kind of flag, and remember, you usually need like OS support to make this flag happen. If we just try to use a variable, then that variable read modify write has to be atomic, right? And this is a read modify write also, right? Read the current status of the flag. If it's not in use, then set it to be in use, right? And if we do that at the same time that this process is doing exactly the same thing, then you've got a resource contention. So in C, we can do something called pthreads, and we can set up mutexes. And we're definitely not going to get into the details of this, and you're definitely not responsible for the details of this. But here's some code that will do this. So we make a structure using something called a pthread mutex. And mutex, semaphores, these are different versions of doing this flag waving, flag detection operation. So I've written a set of methods. One is called mutex init, one is lock, one is unlock. And the idea is we start off, we create some shared memory, and then I say initialize the mutex. And then before I do my increment, I'm going to say lock. Do my increment, do unlock. And so I'm basically just making sure that only one process can do this increment at a time. And so the lock code is a call to this pthread mutex lock function. Unlock is the unlock, and then the initialization is a bunch of stuff that you will do more than your share of in the coming few years at university when you do system programming and things like that. But this is what's happening when we say synchronize, right, in Java. Java object-oriented, we can just say, you know, blah, and a billion things happen in the background. So this is what's going on under the hood, right, in some way, shape, or form. In C, you've got to kind of deal with it yourself, or, you know, use code that somebody has written to deal with it. So we're not going to worry about the details of that, but let's just see what this does. And you have to link with the pthread library. And so if I run this, you know, it works fine. So I'm doing 2 million iterations. The first tally is basically random. And then the second tally should always lock in at 2 million. That was pretty close to the square root of 2, so that's kind of cool. And if you don't do this, right, if we change these things to no ops, right, then it's kind of Wild West. So most languages have some version of a way to do this, right? If you have the ability to run multiple processes or threads, there's something that will support these kinds of locking operations. And it varies from system to system, and most systems have multiple ways to do this. That was kind of cool. The process exited after I got my prompt back. That's kind of special. All right, so that's a high-level view. Don't worry about the C part of it. That's not going to be on quizzes or something. But you should know about synchronizing threads in Java. Synchronized keyword for a block of code or for a method, and some of the basic ideas of when we might need to use that. All right. So let me take a few minutes and let's just talk about the service learning project deliverable. So this is due on that last Monday. I believe it's the 9th. Check Canvas for the date. But your deliverable for this is a report. Okay. This is not like a homework assignment where you just write down, number one and put down the answer and so on. This is a full-blown technical report. Okay, it's the synopsis of what theoretically has been, 2 quarters, half a year worth of work on a project. And it's basically putting this out there to document what you've done. We'll talk about presentations next week, so I'm talking to Izad about this, and we may end up doing presentations in class for the B section. The A section is going to present during the group presentation, and if people from here can make it to that, then I'm going to encourage them to do that. But if not, then we'll probably do presentations during class time that last week. But we'll talk about details. Definitely though, got to do this report, okay? And like I say, this is a formal report. This is something you could hand somebody and they could read it, starting with the beginning, and come away understanding what your SLP was, right? Without ever having talked to you about it, without knowing anything about SLPs or Clark College or anything like that. Okay, it's a full document that stands on its own. And if you're working with other people, everybody should turn in their own copy of the report. You can do one report per group if you like, but everybody needs to submit it through Canvas by the deadline. That's just for grading convenience. And at the very minimum, you need to have these sections in your report. Okay, but this is not even an acceptable minimum, right? You can't just say objectives and then put a sentence. Alternative solutions and put in 2 sentences, right? That's not going to work. So cover page, abstract, table of contents, introduction, objectives, alternative solutions, etc., right? So think technical writing. So among the information that you got to have in there, so describe the problem you're solving, the scope of your solution, right? Background on the problem area, alternative solutions. So if you've done some research and if you know other things in the same problem space, other solutions and so on, compare and contrast those. And then solution specifications, right? This can easily be 20, 30, 50 pages long. This is all the gory details about what you've been working on and what you came up with. So this is, if you've got a circuit, system diagram, block diagram, schematic, wiring diagram, printed circuit board layout, right? Pseudocode, flowcharts, actual code, links to GitLab, all the details, okay? Enough so that, somebody could reproduce your work using this report. How did you test what you came up with? What was your test plan? How did you verify your results? What was the result of testing and trying to verify what you came up with? How did you analyze how good a job you did? So all of the verification and such. Next steps. If you were to continue working on this, what would you do next? What are some of the other enhancements you could make if you had more time? If you're planning to actually continue working on it, you can talk about that. Lessons learned. So, not just about the technical stuff that you learned, but what did you learn about the process? What did you learn about organizing and managing a long-term project, and so on. And then really important, last part, license terms. Right, so if you want this to be available in an open source way where anybody has access to this report, put in some license terms, something like this, right? Permission is granted free of charge to any person, etc., etc. If you want a restrictive license, if you don't want anybody to look at this except for me, who's grading it, and Izad, who's the department chair, right? Make your license terms restrictive. Say, this is proprietary work. You can read this report for grading, but do not distribute it. Do not share it. and we'll respect that. I haven't done the SLP since I came into the Clark system late. How would you apply the solution problem stuff to something like a game that was being developed? That's a big question, but I think we talked about this, and you were going to work on something for 1/4. But shoot me an email, and let's talk about this offline. Okay, cool. All right. So be thinking about that. Get started on that. Don't panic over it, right? This doesn't really involve doing a whole lot other than documenting what you've been doing, which can be tricky to do, and it can feel uncomfortable sometimes. But it's a really good skill to develop. And you know, if you want, I'm the only person who's going to see this, and you know, just pretend you're talking to me and telling me about your project and telling me about these aspects of your project, and you know, just write it down instead of actually telling me. Don't get too worried or worked up over it, but take it seriously. Like I say, don't just turn in a page, you know, with a sentence for each of these things. That's not going to get you any points. Okay, try to make it a document. 1.5 years, cool. Awesome. So if you're coming back next year, so yeah, this is still kind of like, you know, it's the end of the year. It's the June presentation. So yeah, think of it as final in that sense. But you know, under future enhancements, you could say, you know, I'll continue being at Clark, and I'll be taking, you know, other courses, and I'm going to keep working on this, and so on. All right, we are past time, so I'll leave it there. Remember, Monday's a holiday, so I will see you next on Tuesday. Have a good rest of the day. Have a great weekend, and I'll see you next time.